Hello dear students, welcome you all for power system operation and control class. In the previous class we have seen the modes of governor operation. In the asynchronous operation and droop mode operations was seen, and the regulation R was given with delta omega by delta P, that is the change in the speed divided by the change in the power. So we'll continue with the same topic today, and we'll see the different things, and we'll see one problem, and we'll finish the second module today. Fine. So we'll go with one problem now, which is a depends upon the regulation R and all. So you can see the example 6.1 where the two prime movers generators are set parallel. Both have a 3% droop. The frequency is 50 Hz on full load. Plot the speed droop characteristics and comment on the load sharing if generator A is rating of 500 megawatt and the B is having 300 megawatt. So both has got a 3% droop here. So the frequency at the no load is 3% more than the full load. So if it is given as a 50 hertz, 3% more means it is 51.5 hertz. So both A and B characteristics are same because both are having the same droop. So instead of putting the actual values of the load, we have taken the loads in the percentage wise. We can tell the 100%. You can see here at no load, at zero, you see in this figure, it is very clear. At 0% of load, you can see the frequency is how much? 51.5. When it is coming to the 50 hertz, it is giving you the 100% of the load. So here 100% load is the total capacity of the two units, means both units, that is 500 and 300, total 800 megawatt. For any other load, the load is shared is proportional to the capacity, and the frequency is determined by the droop characteristics of the this figure shown. Okay, so if the load is 400, let us assume, obviously A is 250 and B is 150 proportionally we can take, and the frequency is around 50.75 hertz. We can see that in the figure. Okay, so when a number of generators are operated in parallel, the governors of only one set may be in asynchronous mode, all other must be in droop mode. The asynchronous unit is usually the unit with the largest capacity. It controls the system frequency and immediately responds to the system load changes. The unit with droop mode will carry the load depending on their individual speed control. The machine in droop mode are called slave machines. Okay, after the slave machines have been synchronized to the string machine, the load distribution can be adjusted via governor speed control. String machine absorbs the load changes and maintains the constant frequency until the overload or until the output becomes zero. So this is regarding the comment on the first problem. Let us go with the load sharing between the units in parallel. So we can tell the percentage R regulation is defined as the omega NL minus omega FL divided by omega naught. Here the regulation in the change in the steady state speed of the machine is expressed in the percentage of the rated speed. So the omega NL is the no load speed and omega FL is the full load speed and omega naught is the nominal speed or rated speed. Okay, if the governors of unit are parallel had zero droop, then the operating them would lead to instability. So we'll see the one example here with two different machines are working with the uh, different droop characteristics. Here two machines P10 and P20, you can see there clearly. First one is P10, second one is P20 here, and the initial frequency is F0. You can see it in the figure, it's very clear, it is F0 is the frequency. Fine. Now if the load is increased by delta PL, the unit slow down. If load increases, it means speed of the load unit come down, and the respective governors will increase the output until a common operating frequency F1 is reached. Once it is F1 is reached, now the new outputs are P1 dash and P2 dash. You can see it clearly in the P10 when P1 dash is there, in P20 P2 dash is there. This is the new generation. The amount of the load picked up by the each machine depends upon the value of the speed regulation. You can see there is a delta F. Delta F is change in frequency. From F0 to F1 it is come down, that is delta F. So the change in the first power, that is delta P1, is given by delta F by R1. R1 is the regulation of the first unit. Delta P2 is equal to delta F by R2. R2 is the regulation of the second unit. So if we give the delta P1 by delta P2, we will get R2 by R1. So hence the change in output of the generator is thus in the inverse ratio of the speed regulation. You can see it directly. Delta P1 by delta P2 is equal to R2 by R1, inversely proportionalities. Okay. So we'll see one problem here. Here an important problem. Two machines operate in parallel to supply a load of 400 megawatt. The capacities of the machines are 200 megawatt and 500 megawatt respectively. Each has a droop characteristics of 4%. Their governors are adjusted so that frequency is 100% on full load. Calculate the load supplied by each unit and the frequency at this load. The system has the 50 hertz frequency. Now we need to plot the two characteristics. Anyhow, two things are given and two units are with a different power output. So instead of putting it in the actual value, we will put it in the per unit value. So it is very helpful for us. So let us assume that 100 megawatt is a 1 per unit and 50 hertz is a 1 per unit. Okay, frequency base is 50 hertz and power base is 100 megawatt. So full load of unit 1 is 200 megawatt. So obviously it is 2 per unit, and full load of the second unit is 500 megawatt. That is 5 per unit. 50 hertz is 1 per unit frequency. Now the droop characteristics with 4% means when no load is there, it will be having a more than 4% frequency. So 104%. 104% means it is 1.04 per unit. So you can see at zero loading, both the units are at the frequency of 1.04. So first I will consider this first unit, that is having maximum or output of 200 megawatt, that is 2 per unit. When it is coming to 2 per unit, the frequency reaches to 1 per unit. You can see it in 6.11 figure very clearly. Second unit is having 500 megawatt, so it is 5 per unit. It is reaches 5 per unit where the frequency reaches to 1. So this is what the droop characteristics of the two machines. So I think you understood this one very clearly. Now if the load is 400 megawatt, obviously it is 4 per unit. Now let the load supplied by the unit 1 is x. We don't know what power is supplied by the two units. That we what total load is 4 per unit, because 400 megawatt. We will assume that first unit is supplying x per unit, second unit is obviously 4 minus x. Then deviations in the frequency is taken as delta f. From the no load frequency is 1.04. So we will see delta f is equal to delta f by x is equal to 0.04 by 2. So if you put it for the second one, that is delta f by 4 minus x. So you are seen in the just now we are seeing delta p1 is delta f by r1, delta p2 is equal to delta f by r2. Same thing here I have used. Now I am solving for those two equations. I will get that almost 4 minus x by x is equal to 5 by 2, or x is equal to 1.14285 per unit, or x is per unit is actually power. No, obviously it is 1.14285 per unit, means it is 114.28 megawatt. So I got x here. Now what is delta f? Delta f is the 0.02 into x, or because we are knowing that 0.02 of x, it is 0.022857 per unit. New frequency f1 can be given by 1.04 minus delta f, change in frequency or frequency deviation. We will get 1.017 per unit, that is multiplied by 50. We are going to get the 50.857 as the hertz in frequency. So total power supplied by the first unit is x, that is 114.28 megawatt. Remaining power, that is 400 minus unit 1's power generated, is gives you the power supplied by the second unit, that is 285.715, and system frequency is 50.857. The same type of problems are there, 6.5, 6.6 and all. You can try by your own this one. Okay. Now we will see for the deadband of speed governors. What do you mean by deadband? A deadband is in an area of signal range where no action is taken by the controller. This can be inherent or intentional. Inherent deadband is exists because of the minimum value of the speed deviation necessary for this sensor to pick up. Deviation below this are undetected. Means below some deviation, means having some limit, till that deviation happens, no sensors will detect. The sensor detects after some deviations only. The deadband can increase with the wear and tear. Deadband is also introduced intentionally. The previous one, whatever says inherent, now this is intentionally. Intentionally is to prevent the oscillation or hunting. The deadband is around plus or minus 20 millihertz. So this means that if the frequency variation is less than plus or minus 20 millihertz, the governor controller does not act. This implies that the speed change does not result in the change in the position of the governing valves to compensate the change in speed. So this band of frequency where there is no governor operation takes place, a minimum value of the frequency band is given, that is called as dead band of the speed governor. Next, coming to free governor mode operation. When a turbine generator unit is synchronized to grid, every time the grid frequency changes, the unit adjusts its output depending upon the droop characteristics. Say example, if a unit with a 5% droop and frequency dip by 1% necessitates the increase in generation by 20%. Often in developing countries, most of the generators are operating at their peak capacities and no additional generation is possible. Hence, many units do not respond to the frequency dip, causing load shedding action to be initiated. If many units do not respond to the frequency dip, the grid instability may occur. Therefore, it has been made mandatory in Indian grid code, that is to operate free governor mode operation, that is FGMO, according to which generating units are required to increase their generations by 10% for 5 minutes when the system frequency falls. Further, each generator has to provide with the capability of the allow up the 105% maximum continuous rating capacity of the generators whenever the situation requires it. So this is the free governor mode operation. The last part of the second module is actual speed droop characteristics. The straight line droop characteristics is for ideal one. Obviously, we know that is the ideal case. In actual situation, we have a non-linear relationship. Steam turbines have a number of control valves, each having non-linear flow versus position characteristics. Hydraulic turbines having a single gate have a characteristics. You can see here, if ideal means a single line which come down, steam turbines see how like a wave it will go, and hydro turbine is a bigger one wave. So this is what the actual speed drop characteristics. By this, your second module ends. You try the problems of 6.5, 6.7, whatever 6.6, whatever is given. And if you find any difficulties, you can call me. Thank you.